Okay, Assalamualaikum and hi guys. So I will explain on distribution of residence time for chemical reactors. It's chapter 4 in this CRE2, but you may refer to your textbook, the old version of formula, the yellow color, on chapter 13. The new version of formula, you will not have this chapter, so you may refer to Kalam or for the additional information that I've given to you. Okay, so the objectives of this reactor is to define RTD and also mean residence time, to determine ET from tracer data, right? These are the objectives, and write the RTD functions for CSTR, PFR, for ideal reactors, for CSTR, PFR, and laminar flow reactor. Predict the conversion X from RTD data using segregation model. Okay, and then we predict from this conversion, we can also predict the effluent concentration. Okay, so I've divided this chapter into 3 parts that I will do the recording voice. Okay, so now is the part 1, right? Okay. So why are we learning this chapter? Okay, so in a reactor, we have a possible deviation from ideality. Okay, what we call it non-ideal of the reactors. Okay, so in a reactor, for instance, in this figure, we have a stagnant region here. You can see my cursor, right? So some of the flow may not be well mixed. Okay, similar as in CSTR. Okay, they have a stagnant region here, right? So what we call here is actually a short circuit or bypass. So we have another problem such as that volume. So in this chapter, we will define that, okay? So it's not a typical chapter like the previous one that you have learned, okay? So you wanted to know what is actually the problem of your reactor, all right? So these are the topics to be covered, okay? So you will know the general characteristics of the RTD, and then RTD in ideal reactor, and also RTD in non-ideal reactor, and how you model the reactor with the RTD, right? Okay, so first, RTD, residence time. What is residence time? Okay, you can imagine there's a lot of atom, okay? Every atom has a different time spent in reactor. Different time spent in the reactor will give you a different reaction, different output product. Okay, so RTD is the characteristic of the mixing, okay, that occurs in the chemical reactor. Okay, and then what is the purpose of this RTD? Is to diagnose problem, as I mentioned just now, and also to predict conversion or effluent concentration, okay, in the reactors. So meaning if you have non-ideal reactors, they will give you, by RTD, it will determine you the current conversion and also the effluent concentration, right? So for RTD, you can imagine like this figure, okay? You will inject the tracer at the feed. Okay, the tracer must be, sometimes they use color or radioactive material. Okay, the characteristic of a tracer, it will not be non-reactive species. It can easily detectable. Okay, it cannot react with the reactor, or it cannot react with the solution in the reactor. Okay, another important characteristic of tracer, it shouldn't absorb on the wall or surface in the reactor. It best if it is colored, and radioactive materials are most common types of tracer, right? So the tracer will be injected at the feed, and it will travel through the reactor, and then it will come out at the detector. Okay, you will detect it here, meaning that you will take the data here to know, and then you will, when you are doing the experiment, so you will see, you can diagnose the data, diagnose the problem of the reactor from the data that you collected from the detector. Okay, there are two methods of injection. So one is pulse input, another one is step input. Okay, so for your syllabus, we will focus more on pulse input, right? Okay. Okay, now we go to the measurement of the RTD. Okay, so just now I did mention about two methods of injection. One is pulse input, another one is step input. So your pulse input will be, the outcome will be something like this, okay? Right, so when you plot concentration versus time, so it will having this kind of curve, okay? So from this data, you can get your RTD function, which is known as ET. So this is the main formula that you need to know. It's concentration at a particular time over the area under the curve. So this area under the curve is actually the integral of Ct dt from 0 to the infinity. So this is known as ET, right? Right. So for step input, you will have something, step input will have something like this, right? So you notice the difference. This is pulse input. This is step input. Okay, so the drawbacks of using step input is difficult to maintain a constant tracer, concentration in the feed, large error, and it's expensive. So we normally focus on using the pulse input, right? So next is, okay, characteristic of RTD. So remember just now we, in the formula, there's ET. So what we call it as the age distribution function. So this ET, by having this ET, you will directly know what is the problem of the reactor. Okay, because from ET you can determine your mean residence time. Okay. Right, so these are the characteristics that we will use ET. Okay, so we is the integral relationship, mean residence time, known as TM. Variance, this one I think you have learned during your statistical mathematics. Okay, it's just the same thing, right? It's sigma square. Skewness, known as S, normalized RTD function, internal age distribution. So normally we focus on these three, okay? Residence time, variance, and skewness, right? So this is the integral relationship, all right? So ET is actually fraction of effluent spending in reactor for less than time t. So it's equals to FT, right? So now we go to the mean residence time, or known as TM. Okay, so last time during your reaction 1, you know, you met with this term, residence time, TM. So TM is known as tau previously, right? So tau equals to TM. So this can be done only for closed system, okay? So tau, which is space time or mean residence time, is equals to V over V naught, remember? Right? So if you have an experimental data for the RTD, so you can calculate your TM. You may also calculate your TM using this formula. So it's the integral of TET times DT, TET DT, okay, from 0 to infinity, right? So this will give you basically what is your residence time for the reactor to run the reaction, right? So you can compare this TM with the ideal condition of the TM of your reactor supposed to have. Okay, later I will show you some example of it. Okay, so variance is also known as square of standard deviation. So variance is sigma square. Okay, so once you get the variance, you will easily determine standard deviation, right? So this is to indicate the spread of the distribution. You wanted to know how well is your data, right? So this also can be found in your textbook, right? So skewness S to the power of 3 is to measure the extent that a distribution is skewed to one direction. Is it skewed to the left or skewed to the right? So this is the formula. So if you realize just now, okay, it will be very well sequenced. Okay, first, okay, if you remember, initially we need to define ET, right? So once you get your ET, you will see that in defining your TM, you need this ET, okay? Then only you can solve for TM. Then when you have your TM and ET, then only you can solve your variance, right? Same goes for skewness. You need to have TM, ET, and variance or standard deviation. Then only you can solve for S. So it's a sequence. So I will show you some example of it in the part 2 of this video, right? So this is the normalized RTD function. It's used to compare the flow performance inside of the reactors of different sizes. Okay, so normally, for example, CSTR, we use ET is equal to 1 over tau. So at any particular time over the residence time, okay, or space time. Okay, that's all, I think. So we'll see you after this for the example to calculate TM and ET and also variance. Bye.